Hey y'all, today we're going to talk about something called Le Chatelier's principle. So what Le Chatelier's principle talks about is if a chemical system is already at equilibrium, it's already balanced out, we already know its K value, all that good stuff, we can make some changes to that system to push it out of equilibrium, and that reaction spontaneously on its own will try and re-establish equilibrium. But it will re-establish equilibrium with different concentrations or different pressures based on what we have changed about that system. So we're going to talk about four big changes, I think, um, modifications that we can make to that system to figure out how it's going to affect things. So the first big stress or change that we can make to a system that's already in equilibrium is to change a concentration of either a reactant or a product. And so this states that if we add either a reactant or a product to a system that is already at equilibrium, the equilibrium position will shift in the direction that lowers the concentration of that component. So something that I usually say is that we are going to shift away from an addition, or we are going to shift towards removal. So here we've got our good old-fashioned favorite equation, the formation of ammonia from hydrogen and nitrogen. So if I have this system, if I add nitrogen to the system that is already at equilibrium, I add some nitrogen in. Since I am adding in a reactant, that is going to cause my reaction to shift towards the products to use up some of that nitrogen, to use up some of that reactant that I added in, which means that the concentrations of hydrogen, nitrogen, and ammonia are all going to change after that addition. After that addition, when I reestablish equilibrium, my K value is going to help me identify what ratio those products and reactants should be in when equilibrium is reestablished. A little bit later on in this unit, we'll talk about how to do the math when that happens. But for right now, we're just talking about which direction equilibrium is going to have to move in order to reestablish. So if I added in nitrogen in this case, I would shift towards my products to make more products. Let's say instead of adding in nitrogen, I removed some nitrogen from that system. I made there be less nitrogen. That would be talking about a removal. So if I took away some nitrogen, I'm taking away a reactant. That reaction is going to shift back towards those reactants to make up for that missing nitrogen. So if it shifts back towards the reactants, we're going to end up at equilibrium having a higher concentration of reactants, a lower concentration of our product. So there's some math that we can do that. We can see how that's going to affect my Q and my K. Some of the other shifts that we can talk about, if we add a catalyst, adding a catalyst to a system that's at equilibrium is going to speed up the reaction, but it's going to make both the forward and the reverse reaction speed up at the same time. So adding a catalyst has absolutely no net change on the equilibrium for one of these reactions. So this is why we were talking about how kinetics and equilibrium are so very different from each other. Catalyst is going to help us reach equilibrium faster, but it's not going to change where that equilibrium is positioned. We can change pressure, or we can change volume to cause a change in pressure if we have all gases. We can do this in a couple different ways. One way is to either add or remove a gaseous reactant or a product, which is going to behave the exact same way as changing concentration. As a matter of fact, in that reaction, we actually talked about having gaseous reactants and gaseous products. The nitrogen and the hydrogen are gases. So that's just going to act just like before. That reaction is going to shift away from an addition and towards a removal. Sometimes we want a reaction to happen in an atmosphere of an inert gas, which maybe stops other side reactions from happening. Maybe we need there to not be oxygen around because maybe it's going to explode, something like that. When we have an inert gas, or to be totally honest, any chemical that is not in that equilibrium expression, if we add that to our chemical system, there is going to be no effect on the position of the equilibrium. So even though adding that inert gas in this case, or adding something else, is going to change the overall pressure, it's going to change the overall volume possibly, it is not going to change the position of the equilibrium. Possibility number 3 is changing the volume of the container. Back when we studied gas laws, hey, look, here's a throwback. When we know that pressure and volume are inversely proportional. So if I make the volume of my container smaller, then that's going to affect the pressure. That basically is increasing the pressure of those gases. So we're going to behave just like an increase of the pressure. If we make the volume larger, we are in effect decreasing the pressure of those chemicals. Part of what can affect equilibrium when I change the volume, it doesn't work exactly the same way as changing the concentration. Because if I change the volume of the container, I'm changing that volume for both the reactants and the products. So this becomes more of a simplification kind of question. Like if I have a lot more space, I can have a lot more molecules around. If I have an itty bitty tiny space, maybe I need to conserve my space and combine molecules a little bit. So this one, when the volume of the container is reduced, the system is going to want to reduce its own volume also. So by reducing its volume, it's going to shift towards the side with the fewest number of particles, the fewest number of molecules of gas. So if we look at this particular reaction, we're still talking about the formation of ammonia. On my reactant side, I've got the equivalent of 4 moles of gas of reactants, 3 moles of hydrogen and 1 mole of nitrogen. On my product side, I have the equivalent of 2 moles of gas. So if I have less space, I'm not going to be able to have all of these particles that exist on our reactants. I'm going to shift towards the sides that has less particles. So for this particular system, if I increase my volume, I've got more space. I'm going to be able to hold more molecules. I'm going to shift towards my reactants. Because I've got more room, I've got more space available for that 4 moles of particles, basically. If I decrease my volume, I'm going to shift towards my products. Because in this case, I have less particles on my products. If I have less volume, that's going to be able to compact those molecules a little bit more. It's going to save some space. Now, in any different reaction, if I'm not talking about the formation of ammonia, maybe I have more moles of products than I do reactants. That's going to cause shifts opposite directions. But so when we're talking about changes in volume, we're really talking about looking at conserving space in terms of the number of particles. The last change that we can make to a system that's already in equilibrium is to change its temperature. Now, when we are going to be changing temperature, we need one extra piece of information about these chemical reactions. We need to know if these reactions are endothermic or exothermic. And so a lot of times you're going to see this written as a delta H value at the end of the reaction. So if I have an exothermic reaction where I'm forming energy as a product, the delta H is going to be a negative value. If it is an endothermic reaction, meaning I have to put energy into that reaction, energy would act as a reactant, that delta H is going to be positive. So if we think of energy as either a product for an exothermic reaction, or as energy as a reactant, something that's going into that reaction for an endothermic reaction, we can follow our same rules about energy or about reactions shifting away from additions and towards removals. But it's just going to matter which type of reaction I have, whether it's an endothermic reaction or an exothermic reaction. So if I have an endothermic reaction, let's say, which means heat is acting as a reactant. We don't always write heat there, but that's what it means when we need to put energy into that reaction to make it happen. If I increase my temperature, I am increasing a reactant. So I'm going to shift away from that increase. So I'm going to make more products. I'm going to have less reactants. Now, heat changes are going to change my K value. So not only am I going to shift towards the products and make more products, but I also am going to then make my K value larger because I now have more products and less reactants than my original equilibrium. If I have an exothermic reaction, this means heat is a product and I increase the amount of energy in that system, I increase the temperature, I'm increasing a product now. So I'm going to shift away from my products towards my reactants, making more reactants, leaving behind less products. So that is going to cause my K value to actually decrease. So this is a lot of motion of different variables all changing at the same time, but it still all follows our same basic principle of reactions are going to shift away from additions and towards removals. So this chart here is a really nice sort of summary of all 4 different combinations of endothermic and exothermic and increasing the temperature or decreasing the temperature. So when we see chemical reactions, oftentimes we're going to see, here's one, where it gives you the delta H value at the end of the reaction. All we really need to look at is the sign of that delta H. And here that delta H is telling me it's positive. Positive means that this is an endothermic reaction. So I can really think of there being heat or energy acting as a reactant in this case. Right? So pretty much when we're talking about Le Chatelier's principle, there's going to be a whole bunch of questions where it's just like, which direction is this reaction going to shift? You can either say it's going to shift to the left or the right, or we can say it's going to shift towards the reactants or towards the products. Either one of those is an acceptable way to explain that. Lots of times they're also going to ask you to justify your answer. So then we would talk about how. Because this is an endothermic reaction, it's going to behave this way. Or because we're adding in a reactant, it's going to behave in this particular way. Like I said, again, we're going to practice this a bunch in class. And I will talk to you all then. Bye.